Good morning to all of you. In previous sessions, we have seen various properties of Fourier transform. We have seen proofs as well as some examples where we have applied these properties to get the actual Fourier transform. In today's session, we will be discussing relationship of the Fourier transform and the Z transform. So we'll see the relationship of the Fourier transform and Z transform. So as we know that the Z transform of the discrete time signal x of n is simply represented as x of z is equals to, here we are identifying the Z transform of the discrete time signal x of n, where the limit sign is equals to minus infinity to infinity, right, into z to the power minus n, x of n into z to the power minus n. So this is the formula for Z transform. This we have already seen when we discussed the Z transform topic. So for every Z transform there is some ROC, that is region of conversion. So here we can take example as it is maybe between these values, that is R2 to R1, right? So we can represent this variable Z, that complex variable Z, in the polar form, right? So Z can be represented as the combination of real and imaginary values, right? As Z is the complex variable, right? So this Z is the complex variable. So it will be the combination of real and imaginary values. So Z can be represented, Z is equals to, so real value multiplied by this function e to the power j omega, and as we know that e to the power j omega is nothing but cos omega plus j sin omega, right? So it will be the combination of real and imaginary part, right? So this complex variable z is represented in the polar form here, right? So it is represented in the polar form, right? So in this case where this small r, okay, is nothing but the amplitude, okay, or you can also call it as magnitude, okay, and this omega is nothing but the phase, right? So omega is nothing but the phase derived from the complex variable z, okay, so it is phase, right? So if you evaluate this z transform for this value, right, so then the z transform can be written as, so this as I will again write this Z transform formula here, that is x of z is equals to summation n is equals to minus infinity to infinity x of n into z to the power minus n. And if we want to evaluate this Z transform by writing this complex variable in polar form as r into e to the power j omega, right? So that means x of z is evaluated at z is equals to r into e to the power j omega, then this formula becomes summation n is equals to minus infinity to infinity will be as it is, right? This x of n will be there, and in place of z I will substitute r into e to the power j omega, right? So it will be r to the power minus n into e to the power minus j omega n, right? I am substituting in place of z this value, that is r into e to the power j omega, so it will be r to the power minus n e to the power minus j omega, or you can call it as r into e to the power j omega whole raised to the power minus n, right? So I separated those terms here, right? So here if you compare this equation with the Fourier transform formula, so in place of x of n this value is present there, right? Because the formula for Fourier transform, as we know that the Fourier transform is given as Fourier transform of x of n is represented as x of omega. It is equals to again summation n is equals to minus infinity to infinity x of n into e to the power minus j omega, right? So in place of x of n, this value is there, right? So x of z, this x of z can be interpreted as the Fourier transform of the signal x of n into r to the power minus n, right? So that means z transform can be treated as the Fourier transform of x of n into r to the power minus n. So this weighting factor, the weighing factor, that is r to the power minus n, is growing with n. That means if this as n is negative, and if we are considering this value r less than 1, then this r to the power minus n will be growing, and it will be decaying if r greater than 1, right? So this r raised to the power n is growing if r is less than 1, right? If r is less than 1, so that means if it is 0.5, right, 0.2, right, basically r raised to the power minus n is growing with n, right? So if you are increasing the value of n, then r raised to the power minus n will be increasing if r is less than 1, and r raised to the power minus n is decaying if you are increasing n if r is greater than 1, right? Because it will be a negative power, right? So if x of z, this x of z converges for z is equals to 1, that is for r is equals to 1, so that means we can rewrite this equation if capital X of z converges for mod z is equals to 1. Okay, so what is mod z? That means it is a magnitude. Okay, this is nothing but this magnitude or amplitude. Mod z is equals to 1, that means it is nothing but your r, right? So if it is converges for r is equals to 1, then in that case this formula, this x of z evaluated at z is equals to r into e to the power j omega, right? In this case we can substitute r is equals to 1 here, right? So it will be simply equals to summation n is equals to minus infinity to infinity, x of n will be as it is, right? And in place of r you can substitute value 1, so this will be 1. So x of n multiplied by e to the power minus j omega n. And if you look at this formula, so this is nothing but your x of omega simply, right? Correct. So therefore the Fourier transform can be viewed as the z transform of the sequence evaluated at z is equals to n, sorry, z is equals to 1. That means the z transform is evaluated at the or on the unit circle. Okay, because mod z is 1, that means ROC is z is equals to 1. That means the sequence or the z transform is evaluated on the unit circle, right? So while specifying the relationship, therefore the Fourier transform, the Fourier transform can be written as the Z transform of the sequence x of n, okay, evaluated on the unit circle. Okay, correct. So that is the relationship between the Fourier transform and the Z transform. So if x of z does not converge in the region mod z is equals to 1, that is if the unit circle is not contained in the ROC of x of z, that is region of conversion of x of z, in that case the Fourier transform x of omega does not exist. Okay, so this should be the condition, okay, while specifying the relationship between the z transform and the Fourier transform, right? This x of z should converge on the unit circle, that means it should have mod z is equals to 1 value, that is nothing but its ROC. And if x of z does not converge in the region mod z is equals to 1, so what does it mean? That is, if the unit circle is not contained in the region of convergence of x of z, right? The Fourier transform x of omega does not exist for us. Does not exist for us. Okay. So that is the relationship between Fourier transform and the z transform. Here we are simply representing the complex variable z as the polar form variable, that is r into e to the power j omega, where this r is nothing but the mod z and omega is nothing but the angle or phase. Okay, so when we are converging this, evaluating the z transform on the unit circle, that is for mod z is equals to 1, that is nothing but r is equals to 1, so your z transform is nothing but the Fourier transform. Okay, so the existence of the z transform requires that the equation satisfies some region in the z plane. If this region contains the unit circle, the Fourier transform x of omega will exist. However, the existence of Fourier transform, which is defined for finite energy signal, does not necessarily ensure the existence of the Z transform, basically, right? So this we have to keep in mind, right? So in next session, we'll be discussing discrete Fourier transform. Thank you for joining this session.